In this lecture, we're looking at Newton's second law for rotation. What happens when a force is applied to a rigid object that is free to rotate about a fixed axis? Here we show a rectangular object in blue and the fixed axis, the black dot, and a force being applied to this rectangular object. We want to look at the force components on a single particle on the object and in the radial and tangential directions. What I mean is, if we take and put a white dot where the particle is, and we have the force being applied to that particle, we can break that force into two components, a part that is tangential and a part that is radial. What we mean by it, we see that there's a dotted white line connecting the point to the fixed axis, and that the particle is a distance of r from the axis. The radial force lies along the dotted line, and the tangential force is perpendicular to this line. If we look at the force in the radial direction, we see that there's two parts to it. There's the radial part that you're supplying, plus there's whatever internal forces that are involved that hold the object together. Because the particle does not leave the object, F radial plus F internal must be equal to 0. This is what we mean by rigid. The particle on the object is not free to move, so it can in the radial direction, so the net force in the radial direction must be equal to 0. In the tangential direction, the object is free to rotate, so we have that F tan is equal to the mass of the particle times the acceleration of the particle. That's our ordinary Newton's second law. We want to turn this into a version for rotation, so we're going to rewrite this using the angular value for the acceleration in the tangential direction, or in other words, m times the radius times the angular acceleration. If we multiply both sides by r, we have r times f tan is equal to mr squared alpha. And we did that because we know that for a single particle, the moment of inertia is equal to mr squared. And the moment of inertia plays the role of mass in rotation. So then we can replace the mr squared with I, so we have an rf tan is equal to I alpha. And then we can write our Newton's second law for rotation as torque is equal to I alpha, where torque plays the role of force, I plays the role of mass, and alpha is playing the role of acceleration. And we define torque as being equal to tau is equal to the radius times the tangential force, or the distance from the axis of rotation times the tangential force. Let's look at an example. We're going to look at a brake on a stagecoach wheel. We have a stagecoach wheel that is spinning. All the mass of the stagecoach wheel is at its rim, so its moment of inertia is equal to I is equal to the mass times r squared. Now to stop the wheel, we're going to take a block of wood and press it against it. So here you see it come to a stop. The frictional force F is at the rim that stopped it, so it's applied at a distance of r from the axis of rotation, the radius of the wheel. The force is in the points to the left or in the counterclockwise direction, so we'll see that that's going to lead to a positive acceleration, whereas the angular velocity of the wheel was initially in the clockwise direction, which is a negative value. But we'll see that again in a minute. Let's take a look at some equations that describe this. We see that the tangential force is equal to the frictional force, so that r times f tan is equal to r times f. So the torque is equal to the radius times the frictional force, and that's equal to the moment of inertia times alpha. Solving for alpha, we have that alpha is equal to the radius times the frictional force divided by the moment of inertia. Plugging in the value for the moment of inertia, we have the radius times the frictional force divided by mr squared. Simplifying, we have that alpha is equal to the frictional force divided by the mass divided by the radius. Let's look at some numbers. How long does it take the wheel to stop if initially it was spinning with an angular velocity of minus 30 radians per second? In other words, it's spinning with 30 radians per second in the clockwise direction. The mass is equal to 20 kilograms, the radius is 1 meter, and the force that the brake is applying is 60 newtons. The rotational equation for this is the angular velocity will be equal to the initial angular velocity plus the angular acceleration times time. The final angular velocity will be zero because it's stopping. The initial angular velocity is the minus 30 radians per second. Plus, we're going to plug in the numbers that give us the angular acceleration. That's 60 newtons divided by the mass of 20 kilograms divided by the 1 meter radius times the time. Solving for the time, we find that equal to be 10 seconds.